On this video, we are going to explore extrema on an interval. So, relative extrema of a function on open interval. Extrema, when we say, we understand maximum or minimum, and find the extremas on a closed interval. Open interval I just mentioned. So, and in all these, we are going to use first derivative that we learned already. And based on first derivative, we can find out algebraically, let's say not only on graph, but algebraically, we can find out which point is a maximum, which point is the minimum. Is it absolute maximum or absolute minimum, or it's a relative maximum or relative minimum? And what's the difference between these absolute and relative extremas? I have to mention that absolute maximum also we call global maximum or global minimum. So let's take example. Let's say we have this. Okay. And I'm going to draw here some graph function. So what do we have? We have interval, right? Because we have here solid points. And it is closed interval. Okay, closed interval A and B. So let's assume we have 0, 1. Here we have, let's say this is 2 and 5. If it's 2 and 5, then obviously this is, instead of B, I can write down might as well 2, right? And what do we see here? That the point 2 and 5, because we have closed interval, we can find absolute maximum, absolute minimum if they are there. Okay, because absolute maximum and absolute minimum we can have only and only on closed interval. Why? Because what you get. If I would have open interval, then let's say my graph would look like this. And I would have only, on this interval, I would have only relative maximum and relative minimum, because there is no end to this graph. And I have no idea how this graph will behave when it's run to infinity, right? Therefore, so absolute maximum and absolute minimum, or global maximum, global minimum. Let me write down. Absolute max and minimum we can have on closed interval. Well, maybe it's not precisely on interval that is limited, rather saying. What do I mean by that? Let's say, let me see. If I have graph like this, same graph, but a graph of same function, but instead of solid points, yes, I have empty circle where end point is not included, right? That means I will have here interval where the end points are not included, but this is also interval. And in this case, obviously, there is not going to be maximum but minimum only, see, because here it will be minimum on this interval, but we cannot have max here because its endpoint is not included. Okay, so we have here interval, although it's not closed, it's just the endings are not included. All right, so now is it necessary that on a closed interval we will have end maximum and minimum? Absolutely not. Let me show you example. So if I have, let's say it's closed interval, here I have break, empty circle, and here I have this. So this will be absolute max, right? But here we won't have minimum. There is no minimum here. Why? Because we have empty circle. Although the our interval is closed. And here on this graph of this function, we won't have maximum, but we will have minimum. Oops. We will have absolute minimum. Okay? So, are we understanding? It has to be on interval. Let me, to be general, it has to be on interval, because when we have open, it's not an interval. So, when I say we have open, I mean the graph that goes like this, with no limitation, right? No ending. So on the interval, we can have absolute maximum, we can have absolute minimum, or we can have only absolute maximum, or we can have only absolute minimum. And we have example of all of that. So I showed absolute maximum here, and I showed here absolute minimum. Okay, we good? Now, how about when and this maximum minimum we call extreme values. Now let's talk about relative extrema and critical numbers. So when we have graph, maybe I better type. Relative extrema. So when we have graph, and the graph goes like that, so we have open, right? There is no interval. It's a graph that's running to infinity, correct? Positive infinity, negative infinity. In such case, we are dealing with relative maximum, okay? And we are dealing with relative minimum. Okay? So it's kind of hill and valley. All right? So in relative maximum, we can have only when there's no interval. It's running to infinity. Now, my question is, can we have relative, can we have absolute maximum and absolute minimum on this type of functions that running to infinity? No, we can't. But can we have relative maximum and minimum on the closed interval? Yes, we can. And I'm going to bring example. And the reason why we cannot have absolute maximum and minimum on this the function that's running to infinity, because we don't know the behavior of the graph in the infinity. All right. Now, let's say I have such graph. And it's a and enclosed, right? Closed interval. So this is the highest point, right? On this interval. This is gonna be, let me do some more. So we want, like this. So this point is gonna be absolute maximum, although will be other maximum also, but this is the highest one. This is gonna be relative maximum, right? This is gonna be relative maximum. This one is gonna be what? Absolute minimum, right? Because this is the lowest point. So you can have only one absolute maximum, only one absolute minimum, but you can have a bunch of relative maximum or minimums. Besides, absolute maximum and minimum can be on endpoint also. For example, if we look at this one graph, see, we have on endpoint, this is the maximum, right? This is our apps maximum. And it's on endpoint, correct? Or if I have graph like this, let me draw here. This will be my absolute, hold on, no, wait. This is gonna be my absolute minimum, right? And it is on the endpoint. Okay? All right. Now, it's easy to visually see that on the graph where is absolute maximum, absolute minimum, relative maximum, relative minimum, but how to identify that algebraically? Okay? How to identify algebraically? So, what is interesting, when we have maximum, let's say, this maximum, let's say, our slope, it's going to be flat, right? And for horizontal line, and when slope is going as a horizontal line, how much is our slope? 0, correct? And slope is, what is it? It's a rate of change, and it's the first derivative, correct? So to identify algebraically relative extrema, we have to take derivative and then assign that derivative to 0, because at this point, let me show you, at this point we are going to have our derivative equal to 0, because there is no rate of change, right? It's a peak. And if you get the slope, it's going to go horizontal line. Okay. Let's do that, let's show some relative at the maximum or minimum. Let's assume I have such graph. And this graph is f of x is equal 9 times x squared minus 3 and divided by x cubed. Okay, so but on the graph we can see that our relative maximum, we can put its in point, let's say 3 and 2. Doesn't keep proportion for 3 and 2, but let me make sure I keep proportion. If this is 3, let's say 2 is going to be somewhere here. Okay. So it's going to go like that. Okay. And this is going to be 3 and 2. So what we're going to do in this case? We are going to take first derivative, right? So to find the value of the derivative at each relative extremum, we are going to take first derivative. Okay? So first derivative f prime of x, let me remind you here, d of dx for f of x dividing by g of x. Okay, it's equal f prime g minus g prime f and divided by g squared. Okay, and obviously g of x cannot be equal 0. All right, so let's go for it. So first we are going to take the derivative of numerator, right? It's gonna be derivative of 9x squared minus 3 times x cubed minus derivative of x cubed times 9 times x squared minus 3 and divided by x cubed to power 2. Okay, this is gonna be equal f prime of x is equal so it's gonna be 18x because, okay, 9 times derivative of x squared, it's gonna be 2x, and then minus derivative of 3, it's gonna be 0. Therefore 9 times 3 is gonna be 0, right? Or we don't have to put anything, and that's all multiplied by x cubed. Yes. Next, minus derivative of 3x, x cubed is going to be 3x squared, right? And times 9 times x squared minus 3 divided by x to power this 3 and the squared, it's going to be x to power 6. So if we do simplification, it's going to get 9 times 9 minus x squared over x to 4. So if somebody get lost in these simplifications and you can't get the answer, type it in comment and I will go step by step. Okay, so f prime of x is equal 0. Now we are given point 3 and 2. Here 3 and 2. And we need to 3 and 2, and we need to figure out if this is indeed gonna be relative maximum. So, okay, let's see. If I plug f prime of 3, if I plug this 3, I should get 0, right? Because what did I say? When we have relative maximum, relative minimum, there is the rate of change is equal 0, because let's say here it's equal 0 because the slope is equal 0, right? It's flat, it's horizontal line. That's why. Okay. So let me see. I'm going to plug this 3 because this 3 is my value of x, correct? All right, let's do that. So f prime, we clean this 0 and we plug, see if we get 0. 9 times 9 minus 3 squared is going to be 9 and divided by 3 to power 4. There we go. I don't need to continue. 9 minus 9 is 0 and I am getting 0, which means yes, the coordinate 3 and 2 is our relative extrema. The first derivative will not tell us if it's maximum or minimum, because at the point of maximum and at the point of minimum, our derivative is going to be 0. Okay, next example. Let's take example of sine x. So what do we have for sine x? Do I have same? 1, 2, 3, 4. 1, 2, 3, 4. Okay, tiny bit. I can go down. I can do that. Okay, so this is going to be our 1, right? And this is at the point pi over 2, because the graph of sine, that's how it works. Okay, I'll put here. And this one, that's how it works on unit circle. Okay, and this one is going to be 3 over 2 pi. And the result is -1. So 3 over 2 pi -1. This one is going to be pi over 2 and +1. Okay, so we have f of x is equal sine x. So f prime of x going to be equal cosine x, because derivative of sine x is cosine x. All right, well, let's check. At the point of, what do we have? At the point of half a pi, the derivative, first derivative is supposed to be 0, so that will be relative extrema. And at the minimum point, relative extrema minimum, also supposed to be 0. Okay, first derivative is cosine, right? So let's see, cosine half a pi. How much is it? If I take this is 0, this is half a pi, this is pi, and this is 3 over 2 pi, right? Okay, cosine represent our x cosine x, and y is represented as a sine x. Let me see. I'll put this point, pi over 2, and this is sine x. So if cosine x represent x, so how much will be cosine x at the point half a pi? Meaning, if I translate to the graphing language, how much will be x at this point here? It's going to be 0, right? And cosine half a pi also going to be 0, which is true, because derivative, which is cosine, has to be 0 at the point of extrema. And the same thing is here. How much is cosine here? It's also going to be 0, right? So cosine 3 over 2 pi is equal 0. Now don't get confused when you are looking here, comparing why is it not negative 1, 0, why is it not 1 and 0, because don't forget this is sine x, this is not cosine x. Cosine x is a derivative. Okay, so we learned that at each relative extrema, the derivative is equal 0. But we will have derivative 0. No, because sometimes some derivatives do not exist. For example, if I have graph like this, remember we learned, actually, I don't know if I have recorded that video, but just so you know, actually yes I did, but when it's regarding polynomials, when we wanna identify if this polynomial is a function or not a function. So polynomial is defined as a polynomial when there is no sharp corners, like here. If we have sharp corners, then this graph is not a function, and which means this graph does not represent polynomial. And if it doesn't represent polynomial, and poly meaning many terms, that means it doesn't have any extrema, maximum or relative relative minimum, relative maximum, and because at the point of C, f prime of C does not exist. So every time when you see this some sharp corner, then you can know that there is no extrema in that point. Okay? But other than that, if we have soft, smooth, smooth turnaround, then there is extrema f prime of x, f prime of C does exist. Okay, and the slope, which is rate of change at this point, it's gonna be 0, right? Because it's a flat at the horizontal line. All right. All right. And what is interesting, that relative extrema can occur only and only at critical numbers. And this is critical number and this is critical numbers, but both of them are critical numbers here. But in one case, the derivative doesn't exist, and in another case it does exist. And relative extrema can occur only at critical numbers. Okay. So what we can conclude from here? that if f of x has a relative minimum or relative maximum at the point of x is equal c, then c is a critical number of f. So c is a critical number then. Critical. Okay, I am done explaining. This will be part 1 video. In the next video, part 2, I'll just do practicing problems. So you will see how to find extrema, how to plug the values, and so on. Just we'll do practicing problems. See you in next video.